Good morning, everybody. 17A. Hope you're doing all right. Let's see. Let me get you guys the attendance link. There it is. Do the thing. I'll post it up again in a little bit. Let's see here. If there's something else I wanted to say, it's escaping me at the moment. So you guys have started talking more about derivatives. Specifically, he talked about the derivative last Friday of sine and cosine and the exponential functions. So I guess I should just say, do you guys have any questions, either about the current homework or about what's going on in class? Oh. Sure. So I'll do a similar example. We kind of talked about this one last time, but it was kind of at the end of class. So the whole idea with number 4, in fact, let me think for just a second if I want to do something slightly. Yeah, I'm going to make it a little bit different, but that's all right. The idea is going to be the same. So let's say we have this function. So we have f of x equal to, let's go, tangent of 5x over 4x when x is not equal to 0. Oh, tangent's a bad choice. Well, I'll go sine, and we'll go sine. Let's say we have this function. And I just want to point out, this function is continuous everywhere except for 0. Right? It's defined everywhere, the limit's fine. For example, this is definitely continuous at x equal to pi. Because f of pi exists, right? F of pi is just sine of 5 pi divided by 4 pi. Sine of 5 pi is 0. 0 divided by any non-zero number is just 0. And 2, the limit as x approaches 0 of, well, this one actually, the 0, sorry, just got off track there. The limit as x approaches pi of this function exists. Or we look at the limit as x approaches 0. Sorry, I keep saying 0 because that's what I'm going to do. As x approaches pi of sine of 5x over 4x. Well, again, we have this direct substitution rule that basically says if, that's annoying. I'll have to fix that later. Sure, sorry. We have this rule that says if you're taking a limit of something and you can just plug it in to get a number out, you do that. Here you can plug in pi and you'll exactly get sine of 5 pi over 4 pi, which is 0. And then since the function exists and the limit exists and they're the same, we get to say the function is continuous. So these two things together mean, oh yeah, f of x is continuous at x equal to pi. Because the function exists in the 0, the limit exists in the 0, and those two values are the same value. They're both the same. On the other hand, question 4 is asking us to kind of pick what the function should equal at 0, so the function would be continuous. So I'm going to erase this so we can do it. So here's what we want. We want the function to be continuous at x equal to 0. So we need two things to be true. The first thing, we need f of 0 to exist and to be something. And in fact, this is what they're asking us to define. They're asking us in this problem to say, okay, what should f of equal 0? Well, it should equal, what should it equal? Well, we also know the limit has to exist, right? We need the limit as x approaches 0 of f of x. That should exist. It will exist. We're going to find it in a second here. And here's the thing. It's kind of extra squeaky, it seems like. If this limit exists, so I'm going to tell you what it is. This limit exists and it's 5/4. So we're going to show the work. Eventually, we're going to get over here and we're going to get 5/4. So if this limit is 5/4 when x is approaching 0, and I want the function to be continuous at 0, what does f of 0 need to equal so that the function is continuous? Anybody? Anybody? Yeah, exactly. 5/4. Right? The limit and the function have to be the same. So the problem, they're saying, well, we want you to tell us what the function needs to equal so that it matches with the limit. So what they're really asking you in a very kind of long roundabout way is to find the limit. To find the limit as x approaches 0 of the function. I think it's sine of 3x over x. And then after you find that limit, that's the value that this should equal. So we know this is going to equal 5/4 because it's the value we're going to find for this limit. And the way we're going to find the limit is the way we were doing it last time, using what I call the wish method, where we rewrite this as the limit as x approaches 0 of sine of 5x over blank times blank over 4x. And then, what do I wish was beneath sine of 5x? Yeah. Then if I divide by 5x, I also have to multiply by 5x to cancel it out. And then the x's cancel here. And the limit as x goes to 0 of sine of 5x over 5x, since these are the same, and both going to 0, this is going to be 1. So I get 1 times 5/4, which is 5/4. So then the answer to the question, one second, the answer to the question that they're asking, or that I'm asking, would be, we want to define f of 0 equal to 5/4 so that the function is continuous at 0. Now, how do I know the limit as x goes to 0, sine of 5x over 5x is equal to 1? It's a good question, Shayla. That's something we talk about a lot. So I don't want to do the whole kind of, so there is a geometric proof we did of it in class probably like a week ago. And Sandra also did a geometric proof, which is slightly different, but also the same. But the idea here is just in general. So here's what we have. If you have the limit of some stuff going to 0 of sine of that stuff over the same stuff, right? So really, really important here. These two things have to be the same. So if those are the same, then this limit is equal to 1. Oh, I should say, if they're the same and going to 0. So I mean, you're not exactly wrong, Gabriella, but it's not, it's more because of it. It ends up working out that way most of the time. But I want to really I want you to think about it in a slightly different way. It's not that it's because exactly, and I'll show you kind of a counterexample. It's not exactly because I have 5 over 5x over 5x, although it does kind of work that way. It's because this is going to 0 and this is going to 0, and they're the same. So this thing in parentheses is going to 1. And then we also have the 5/4 that are going to balance it out. So for example, the limit as x goes to 0 of sine of 3x over 3x is equal to 1. Because 3x is both in the sine function and in the denominator, and 3x is going to 0. Because if x is going to 0, then 3x times x is also going to 0. So I want to point out this limit's 1. And really, you could put anything in there you want, right? I could write, the limit as x goes to 0 of sine of 17x over 17x. Not very exciting. Same idea. Still going to be 1. You can even make it a little more weird. You can make it something like the limit as x approaches 2 of, I don't know, 20x. Oops, I need the sine. Sorry. of sine of 20x minus 40 over 20x minus 40. So the question, the things you have to look for are, is the stuff inside the sine function the same as the denominator? Clearly, yes, they're obviously the same. And the second important part is, are they both going to 0? Well, if x is going to 2, then 20 times x minus 40 is going to 0, because 20 times 2 minus 40 is 0. So this limit would also be 1, because you've got sine of some stuff over the same stuff, and the stuff is going to 0. Okay, one more. Here's a slight kind of counter example. This one trips people up often. The limit as x goes to 0 of sine of 1 over x over 1 over x. This limit is not equal to 1. And the reason it's not equal to 1 is because even though you have sine of some stuff over the same stuff, and even though x is going to 0, it's not what we need. We need stuff is going to 0. And here, 1 over x isn't going to 0, right? If x is getting really, really small, 1 over x is getting infinitely large. So this is not 1. It's actually equal to 0. You can use the squeeze theorem to show it's equal to 0. So hopefully that kind of clarifies your questions. I did want to do one example. So to kind of go along with what you were saying, Gabriella, I want to kind of come back around and say it's not, you can't always look at these coefficients and get the answer just by dividing them, although it works a lot. So for example, in the actual homework question, where I think it's sine of 3x over x, the limit is just 3, because 3 over 1 gives you 3. But sometimes people, and this, I don't know if Sanders is going to go this way, but we'll do one example. If you had an example like this, where sine squared of 3x over 2x squared. This limit is not equal. So I'm going to contrast this with something else. So we'll do two different ones. Let's use different colors. So compare this with limit x goes to 0 of sine of 3x squared over 2x squared. And we'll actually do the right-hand one first. So the right-hand one is what you think it would be. It is equal to 3 halves. And again, we would do this in the usual way. I would write this as the limit as x goes to 0, sine of 3x squared over blank times blank over 2x squared. And then I'd fill in the blanks. What would I fill in the blanks with? What do I want beneath sine of 3x squared? Yeah. If I divide by it, I also have to multiply by it. And then you can see what's going to happen, right? This part, the limit as x goes to 0 of sine of 3x squared over 3x squared. That part's just going to equal 1. And then these cancel, and you get 3 divided by 2. This problem is not the same problem. Sine squared of 3x means sine of 3x times sine of 3x. So I actually like to write this one out as the limit as x goes to 0 of sine of 3x over blank times sine of 3x over blank times blank over 2x squared. And now I'm going to ask the same sort of question. What do I wish was beneath sine of 3x here? A 3x. If I put a 3x there, I need a 3x up here to balance it out. What do I wish was beneath sine of 3x here? Oh, also 3x. Put one down here, I need another one up there to balance it out. So looking at this, I can do a little rewriting if I need to, but what's going to happen is the limit of this part's going to be 1. The limit of this part's going to be 1. And this part's going to reduce. Well, the x times x on top is going to cancel with the x squared on bottom, and we get 3 times 3 over 2. So my answer ends up being 9 over 2, not 3 over 2. So just something to be aware of. Are there other questions about the homework that you guys have? Okay, question 3. We can definitely look at question 3 too. And again, I'm going to make up one that's a little bit different. So what I want to point out for both question 3 and 4 is the whole idea is that they're using the idea of, or the definition of what it means for a function to be continuous to find the thing they're asking for. So let me do something slightly different. Actually, let me see if I can grab an example from another textbook here. Because sometimes there are good examples. 1 second, please. That could be fun. Sure. Yeah, we'll do 2. We'll do a less exciting and a more exciting one. Right. Okay. Let's say our function was this. F of x is equal to, what have we got here? X cubed when x is less than or equal to 2. And that's going to be disappointing. Let's say, fine. A times x squared when x is bigger than 2. We want to figure out what a needs to be so that this function is continuous. Now, what I need to say about this is there's kind of a short way of doing it, and then there's a more correct way of doing it. So the short way of doing it is to plug in 2 into each of these pieces of the function. So if I plug in 2 to the top piece, I get 2 cubed, which is 8. I plug in 2 to the bottom piece, I get a times 2 squared, which is 4 times a. And the thing is, these two things need to be equal to each other when we plug in 2. So if these need to be equal, you can set 4a equal to 8 and get a equal to 2. And that's kind of the fast way of doing it. However, I really feel compelled to mention, usually people want to see more work. What they want to see is the fact that you're using the definition of continuity. So the things I would probably say if I was doing this on a test, or even on a homework assignment I was turning in, I would first, so again, we're trying to be continuous at x equal to 2. And to be continuous somewhere, the 3 things have to be true. The function has to exist there, the limit has to exist there, which is what this is kind of revolving around, and then they have to be equal to each other. So first things first, f of 2, I would plug 2 into the top piece, because that's where x is equal to 2. So f of 2 is going to be 2 cubed, which is 8. Second piece, the limit. So to do the limit, I need to do the left-hand limit and the right-hand limit. So the limit as x approaches 2 from the left. Okay, quick question. If I'm approaching 2 from the left, am I using the top piece here or the bottom piece here?
Top.
Exactly, yeah, because that's where x is less than or equal to 2, and 2 from the left is less than 2. So we're using the top piece, and then you're just plugging in 2, right? Whenever you're taking a limit, you always just try and plug it in. If you get 0 over 0, then you have to do more work. But if you don't, you're done. So I plug in 2, I get 2 cubed, which is 8. But then I have to also do the limit from the right-hand side. So the limit as x approaches 2 from the right. Well, from the right, I'm going to use the bottom piece because that's where x is larger than 2. But again, I just get to plug in 2 for x. I get a times, 2 squared, which is 4a. And then for the limit to exist, the left-hand limit and the right-hand limit have to equal each other. So since these have to equal each other, we're getting 4a equal to 8. So a is equal to 2. And then you could say more, right? You could say the limit, the function is equal to 8, the limit's equal to 8, since they're the same, it's continuous. I don't really think you have to say that at that point. So you can kind of see, this is the work I would probably expect him to expect you to do. Right? Like you would want to say that specifically, I would say if I had him be continuous to 2, really the limit needs to exist. Meaning the left-hand limit and the right-hand limit have to be the same. This is the shortcut way of doing that though, right? For these functions, the left-hand limit we just got by plugging in 2 to the left-hand piece. The right-hand limit we ended up getting by plugging in 2 to the right-hand piece. So if they're functions where you can just plug in the value where you're broken at, usually you can just test those that way and then set them equal to each other. Okay, let's do a slightly more challenging one just because it's good to. This was I always keep thinking it would not surprise me if he had some test except giving you midterm. So yeah. Still, that kind of question or this next kind of question is not unreasonable for an exam. So let's take a look at this question I've got here. So let's say our function. Fine, I'm gonna make it more interesting. Let's say our function f of x is equal to what have we got here? Sorry, where'd you go? Apologies. Sure. Let's say it's x minus 3 when x is less than or equal to -1. And then it's ax plus b when x is between -1 and 3. And let's say it's x, so it's 7 minus x squared when x is greater than or equal to 3. This one is a little more complicated, but it's still the same idea. So we want to find values for a and b so that the function f of x is continuous everywhere. Now, I'll just say, we know it's continuous everywhere already, except for -1 and 3. Can you guys see that all right? It looks kind of small to me, but I guess it's not too hard to see. Okay, I'm just far away from my screen, so. So this function, x minus 3, is definitely continuous on its domain. This function, 7 minus x squared, is also continuous on its domain, and so is ax plus b. If they're all polynomials, they're all continuous on their domains. The only potential issues are when we switch from one to the other. So really, we have to figure out the limit at -1 and the limit at 3, because we need those to exist for the function to be continuous, or to be able to be continuous. I'm not going to worry checking about if the function exists. I know f of -1 exists. It would be whatever I got when I plugged in there. And I know f of 3 exists. It would be whatever I got when I plugged in there. So I'm just going to go straight ahead defining the limits. So at x equals to -1. So the limit as x approaches -1 from the left, I'm using that piece of the function, right? X minus 3, because that's when I'm left of -1. And I'm just going to plug in -1 and get -1 minus 3, which is -4. And I approach 1 from the right, sorry, -1 from the right. So limit as x approaches -1 from the right. I'm using this piece now, except for x is bigger than -1. And I'm just going to plug in -1 for x. And all I'm going to get is a times -1 plus b. Or I probably write that as b minus a. So here's what I have so far. These have to equal each other. So b minus a has to equal -4. But that's not enough, right? I don't know what a and b are yet, right? B could be 1 and a could be 5, but maybe that's not right. I need the other piece of information. So then I'm also going to look at x equal to 3. Say, okay, the limit as x approaches 3 from the left. If I'm left of 3, I'm less than 3. So I should be using this. I'm just going to plug in x equal to 3. You get a times 3 plus b. And then the limit from the right, as x approaches 3 from the right, I'm going to use this piece where x is bigger than 3. So I'm going to do that function, 7 minus x squared. That's going to be 7 minus plug in 3. Minus 3 squared, so 7 minus 9 is negative 2. So here's what I got here. 3a plus b equals negative 2. And then I would probably solve each of these for b and set them equal to each other, or solve one for b and plug it into the other one. So I might solve for b here and say, okay, b equals a minus 4. Plug that in over here. So 3a plus a minus 4 equals negative 2. So then 3a plus a is 4a minus 4 equals negative 2. Add 4. 4a equals 2. A equals 2 divided by 4, which is 1/2. And then going back over here, b is going to be 1/2 minus 4. That's 1/2 minus 8/2. So b is equal to negative 7/2. And those would be the values of a and b that would make this particular piecewise function continuous, because they made it so the limit exists. I should say the limit existing is not alone a sufficient condition for continuity, but we already know that if you plug in, -1, you'll get this part equaling -4, and these values will also make this part -4. So you really, for this kind of question, you really only have to check if the limit from the left and the limit from the right are the same for each part. So hopefully that helps you figure out how to do problem 3. It's the same sort of idea. You're going to take the limit as x approaches 1 from the left, limit as x approaches 1 from the right, and then set those equal to each other to find out a. My guess is that you should get a equal to -3, but I'm not positive, so you should definitely check that. Are there other questions regarding the homework? I know we looked at a lot of it last time, but I'm happy to address any other questions. Or I can start talking about derivatives. 9. So we definitely talked about 9 last time as well. Not that I won't talk about it again. So I'm going to do a different example. So last time I think the example I did was a little bit tricky. I'm not going to lie, it was challenging. Well, also I should just mention I posted a quiz for you guys. It's not. I've changed the due dates on the quizzes. I think maybe so it's not due until like tomorrow night at midnight. So you got plenty of time for the quiz. Just because I feel like you shouldn't have to be so urgent about it. We definitely do the quiz. There's some good derivative questions on there, I think, that will. There's also some examples that will kind of help guide you through it. So I want to find the equation, the limit definition of the derivative to compute the derivative of. So I'm going to make up something completely different. I want to find the derivative of f of x equal to, what have I got here? I don't know. The square root of 2x plus 1. That's so boring, James. Sorry, I always come up with the same examples. They get old. Let's do 2x plus 7 at x equals to 9. So I want to find the derivative of this function at x equal to 9. So here's what you have to remember, first and foremost. We're using the limit definition. So the derivative, and I'm going to write two things. First, I'm just write f prime of x. So f prime of x is the derivative as a function. We're actually not going to do it that way here, but you should be thinking about this. That's the limit as h goes to 0 of the square root of 2 times x plus h plus 5. Sorry, I skipped a step. Let me not skip a step. Let me write just the regular old. It's limit as h goes to 0, f of x plus h minus f of x all over h, which is just the difference quotient that we're taking the limit of. And then if I was actually going to plug in my function, so it would be the square root of 2 times, not x, but x plus h, to be the square root of 2 times stuff plus 7. The stuff is the x plus h, minus the square root of 2 times x plus 7, all over h. And that's how you would set up the limit definition as a function. Sorry, you said, oh, sorry, that's something else. So the idea for this particular example is instead of actually doing it that way, although we could totally do it that way and multiply by the conjugate and get some function of x, if you're finding the derivative at a point, you can say, well, okay, I'm going to find f prime of 9 is going to be the limit as h goes to 0 of f of 9 plus h minus f of 9 all over h. Same idea, just we're actually using numbers instead of variables. So the limit as h goes to 0. So I'm just replacing all my x's with 9s. So I'm going to have the square root of 2 times 9 plus h plus 7 minus the square root of 2 times 9 plus 7 all over h. But then we're meant to evaluate this. And I'm going to say this over and over and over again. Whenever you're doing a limit definition of a derivative, our end game goal is to always cancel out this original h in the denominator. And our intermediate goal is to make sure that all the not h's in the numerator cancel out. Now for this problem, for any problem where you have a square root plus or minus something else, you're going to have to use the conjugate. So two things I would do. Well, one thing I would do, I would first simplify that second square root. So when you're doing the derivative at a point instead of just x, you can usually simplify the f of 9 part, or the f of whatever, right? Here you can't simplify f of x on top, right? Like this here doesn't get any simpler, the square root of 2x plus 7. But this here does, right? The square root of 2 times 9 plus 7, that's 18 plus 7, that's the square root of 25, which is just 5. So I'm going to rewrite this as the limit as h goes to 0 of the square root of 2 times 9 plus h plus 7 minus 5 all over h. And then I'm going to multiply by the conjugate. So we're going to multiply by the conjugate, which is this, instead of being the square root minus something, it's the square root plus something. Or you always change the sign of the connecting between the square root and the other thing. So I'm going to multiply by the square root of 2 times 9 plus h plus 7 plus 5 over the same thing. Okay, so when you do this, when you multiply conjugates together, you always get the first thing squared. That's just going to be 2 times 9 plus h plus 7 without the square root. The middle terms cancel, and then you get minus the second thing squared, which is just 5 squared, or 25. All over the bottom, which is h times all of that. Square root of 2 times 9 plus h plus 7 plus 5. Okay, let's see what happens on top. So on top, I'm going to get, let's see, the limit as h goes to 0 of 2 times 9 is 18, plus 2 times h is 2h, plus 7 minus 25. All over the same denominator. H times the parentheses square root of 2 times 9 plus h plus 7 plus, I think I made it, no, that's right, sorry, plus 1. Okay, oops. I'm going to do a little, I know, so I'm almost out of room, so what I'm going to do is I'm going to do a little work here. You can hopefully see that 18 plus 7 is 25 minus 25. Those all cancel. So I'm really just left with 2h over h times all this stuff. And then, since all the non-h things canceled, the remaining h, you can factor out the h, there's only one time you'll have to factor it out. This h on top would cancel this h on the bottom. And then, and only then, after you've canceled out the h's, the rest of the h's you can plug in the 0 for. So I'm going to get 2 over the square root of 2 times 9 plus 0, well, that's just 9. So 2 times 9 is 18 plus 7 is 25. Square root of 25 is 5. The square root of 25 plus 5, which is just 2 over 5 plus 5, 2 over 10, which is 1/5. So that's the very general kind of idea here, is you're starting with f prime of whatever number you've got. So I think they're asking you for f prime of 1. So you do f of 1 plus h minus f of 1. And so not to do the whole problem for you guys, but just to start it out. if I was doing that problem, problem 9, where f of x is 1 over x squared, and you're at x equal to 1, I would start off by saying, okay, f prime of 1 is the limit as h goes to 0 of f of 1 plus h minus f of 1 all over h. And then I would actually plug it in. So, sorry, I should miss the whole word. So you're going to get, let's see, f of x is 1 over x squared, so f of some stuff. One over, instead of x squared, it's 1 plus h squared. Minus f of 1 is 1 over 1 squared, which is just 1 all over h. And then you're going to want to multiply by a common denominator. So I'm going to stop there. The next step would be to multiply both the top and bottom by 1 plus h quantity squared. And you can distribute there, and you'll get 1 minus the quantity of 1 plus h squared. So I think from there you should be able to finish it off. What should happen after you do that is the things on top, the not h things should cancel out, and the remaining h things should, you should factor out an h and cancel out the h in the bottom. Okay. Someone said question 6. Sure. Fine. So let's look at 5 and 6. So 5 asks us to find the average rate of change of a function. So let's, of course, look at a different function. I'm going to look at the function. What have I got here? Sure. 36 over the square root of x on the interval from that's less exciting than I wanted it to be. Let's do the interval from 4 to 144. Sure. We want to find first the average rate of change. The average rate of change is just another name for the slope of the line connecting the 2 points. Right, so when you're finding the average rate of change, you can do it like this. You can say it's f of b minus f of a all over b minus a. Right? That's how you find average rate of change between a and b. But here's the thing. That's just a way of writing the slope between 2 points. If I actually draw, and my picture is not going to be great. Let's see. Sure. So here's 4, and here's 144. And my function maybe does something like this. But here's the thing, right? This point here is the point 4 comma f of 4. And this point here is the point 144 comma f of 144. So when I calculate f of 144 minus f of 4, that's the difference in the y's, divided by 144 minus the 4, that's the difference in the x's. I've got the change in y over the change in x. That's just the slope of the line that goes with those 2 points. So the average rate of change is just another name for the slope of the secant line, and it's going to be f of 144 minus f of 4 all over 144 minus 4. So in this case, so let's see, if I plug in 144, what's the square root of 144? Everybody. Oh yeah, the attendance, sorry. I'll send the attendance. Yeah. Square root of 144 is
12.
12. And then minus f of 4 is going to be this 36 over the square root of 4, which is just 2, all over 144 minus 4, which is 140. Simplifying, 36 divided by 12 is 3. 36 divided by 2 is 18 over 140 minus what? 40. So I end up with negative 15 over 140. which I would probably, yeah, you can reduce that. That reduces to -3/28. And you can probably find it as a decimal as well, but I would probably leave it as a fraction. So that's how you find the average rate of change. And then to answer the second part of that question, so question 6 for this function on this interval, if I was trying to find now, so let's see, so we found the average rate of change of our function on the interval from 5 to 10. Now we're going to compute the secant line of this function, f of x equal to 36 over the square root of x between x equal to 4 and x equal to 144. But the thing is, we've already done most of the work. Here's the attendance again, because I think I just heard someone come in. We've already done the majority of the work. We found the slope of this line, right? The slope is still the slope. We're trying to find the equation of that line right there. That is the secant line between x equals 4 and x equals 144, the line between the corresponding points on the graph. So we already have the slope is -3/28. And then you can pick either, well, so there's actually two ways you can do this. I personally prefer to do it this way, but I'll show you the other way as well. I would do it as y minus, pick either point. Pick either 4, comma, if you plug in 4, we found that we got, sorry, I forget, 18. We didn't actually find it. Well, yeah, we did, right. If you plug in 4, you get 36 over the square root of 4, which is 18. Here, if you plug in 144, if you plug that in, you get 36 over the square root of 140, which is 36 over 12, which is 3. So use either one of these points. I'm going to use this one and say y minus the y value equals your slope times x minus the x value. And I personally like to just leave it like that. But if you don't like that, that's fine. Yeah, I'm going to erase this. You can solve for y. You can say y equals, I'm going to distribute this -3/28. You get -3/28 x. -3 times -4 is +12/28. And then I'm going to add this 18 over to the right-hand side. And then you should probably combine those two, right? 12/28 plus 18 is not pretty, but you end up getting y equal to -3/28x plus, let's see, 18 in terms, well, actually, we can be smart. We could reduce this fraction. This reduces to 6/14, which reduces to 3/7. So 3/7, and then 18 times 7 over 7 is 70, 48, 118. So you've got 3/7 plus 118/7, which is 121/7. Not the prettiest numbers I've ever come up with. So that's definitely one way you can do it. The other way people prefer to do this is to start with the y equals mx plus b, and then plug in one of those points to get the value for b. So you can do it as, y equals m x plus b, or we already know the m value. And then we plug in one of the 2 points we just used. So I'm going to use the same point and say, okay, y is 18, and x is 4. And then we can use that to find our b value. So finding b, let's see, 18, I'm going to add this over here. So, right, because this is -3/28 times 4, it's going to be +3/28 times 4. But again, right, I can cancel. So I've got 18 plus 3/7 plus b. And then I'm going to multiply 18 by 7 over 7. Right, because that's 18 over 1. And 7 times 18 is 70. Oh, I made a mistake up there. That should be 118. 7 times 18 is really 70 plus 56, which is 126. So I get 129/7 for my p value. which is what it should have been up there, but they made a small mental math error. Right? This 18 times 7 should have been 126 sevens, which means I should have gotten 126 plus 3 is 129 sevens. Sorry about that. So we would get b equal to 129 sevenths, and we could plug it back in and say, oh yeah, we've got y equals to negative 328x plus 129 sevenths. Either way of doing this is fine. It's really just a matter of personal preference. So yeah, so for problem 5, same sort of idea, right? You're gonna find the slope by doing the difference in the y's or the difference in the x's, and then you're gonna find the equation by for problem 6 by using that slope in problem 5, and then just either finding the equation of the line by doing the point slope form or by doing dy equals mx plus d form. Either way is fine. Okay. So let's see, we got about 4 minutes left. So let's just, so I want to talk real quickly. So derivatives as functions is definitely where we are at in class. It's definitely what he's been talking about for the last 2 days, and I imagine he's going to go further today. And so I don't think we have time to say all the things right now, but I'll run down just a couple things, and then on Wednesday we can talk more in depth about them. So here's what he said so far kind of about derivatives. So if you have some function like x to the 4th, the derivative, there's this thing called the power rule. We can definitely show it next time. The derivative is the power comes down in front, and the new power is 1 less. So that's the power rule as in this specific example. Now there's a couple ways of writing this. He doesn't seem to like writing like this, which is perfectly fine. I don't love writing like this either. The most efficient way most people like to write finding derivatives, they use them to say they write d dx of your function. And what that means is find the derivative of x to the 4th. That's equal to 4x cubed. And so we could ask more challenging questions like, what's the derivative of, I don't know, 2x to the 6th minus 5x cubed? And so we have this power, and sometimes people put parentheses around this, sometimes people don't, and you're just supposed to assume it's the derivative of the whole thing. So what's the derivative of 2x to the 6th? Well, in addition to a power rule, there's also this constant multiple rule. It says if you have a constant times a function, the derivative is the constant times the derivative function. So what's the derivative of x to the 6th? 6x to the 5th. Minus 5 times, what's the derivative of x cubed? X squared. What ends up happening in practice is you don't really just say, oh, it's 2 times 6x to the 5th. You just say, oh, well, the 6 is going to multiply the 2, and you're going to get 6 times 2 is 12x to the 5th, minus 5 times 3 is 15 x squared. And that's how you would find the derivative of a function like that. So I didn't even say it, but I just used the sum and difference rule for derivatives. If you're taking the derivative of a bunch of things added or subtracted together, you just kind of treat them individually and then add or subtract the results. So 2 last examples. If I wanted to find the derivative of x to the 5th plus 2x to the negative 3rd minus sine of x, I would just treat them each individually. So the derivative of x to the 5th is 5x to the 4th plus the derivative of 2x to the negative third. Well, I'm going to use the power rule. The negative 3 is going to come down. It's going to multiply the 2. I'm going to get negative 3 times 2 equals negative 6 times x to the, what's my new power going to be? What am I going to get for my new power on x? I'll give you guys choices. Yeah, good, excellent. Great. The reason I asked that one specifically is because a lot of times people make the mistake of saying it's negative 2, but it's not, right? You're subtracting. When you subtract from a negative, it should get more negative. And then finally, you talked about in class on Friday, the derivative of sine of x is cosine of x. We don't have time to explain why right now, but definitely on Wednesday, we can talk about why the derivative of sine is cosine and why the derivative of cosine is sine. And it's actually, he didn't do this in class, but it's really nice if we actually look at the graphs of sine and cosine. So what I would, before class on Wednesday, I would like all of you to remind yourselves of what the graphs of sine and cosine look like. And then we will talk about that on Wednesday. All right, that's all I have for today. Make sure you fill out the attendance. There's a quiz to do by tomorrow evening. It shouldn't be too terrible. And I think that is all. If you guys have questions, you're always welcome to start a discussion or send me a message. All right, you guys are welcome. Talk to you later.